Welcome to another video of the MOOC Digital Twins, the common future for infrastructure and city. Today we're going to see Module 2.1, an introduction to digital twins. My name is Alejandro Fedaque Diaz. So before going into technical detail, let's just start with a simple question. What exactly is a digital twin? A digital twin is a virtual replica of a real physical object, process, or even a system. It can represent something as small as a single bridge, component, or as large as an entire city. But unlike traditional digital models, a digital twin is alive. It evolves together with its physical counterpart. Sensors and connector devices continuously feed the model with real-time data, keeping it always synchronized with reality. You can imagine, for example, a real-world tunnel equipped with humidity and deformation sensors. The digital twin of that tunnel receives those measurements instantly and allows engineers to visualize how the structure behaves under different conditions. These two-way connections, data going from the physical asset to the virtual model, and insights going back from the model to the asset, makes the digital twin a bridge between the physical and the digital worlds. Thanks to that bridge, engineers, operators, and even decision makers can monitor performance, anticipate failures, and even test new ideas without having to be on site. It's a new way to understand and manage complex infrastructures, one that combines technology, data, and human knowledge in a single system. Now that we understand the concept, let's look at the main components that make a digital twin possible. First, we have the physical asset itself, the real-world structure, machine, or network that we want to monitor. In the image, you can see a dam that we have taken as an example. Second, we create a virtual model often based on building information modeling or 3D scanning. This digital representation can be highly detailed or simplified depending on the purpose of the twin. The third component is data connectivity. Sensors installed on the real asset collect data, temperature, vibration, traffic, energy consumption, and so on, and transmit it through the communication networks such as Wi-Fi, fiber, or even 5G to the data server. This data flow is what keeps the virtual and physical worlds aligned. And finally, we have the analytics and simulation, the intelligence of the system. Here, algorithms and predictive models analyze the information to detect patterns or to test what-if scenarios. For example, the digital twin of a bridge might simulate what happens during an earthquake and how fatigue accumulates in steel members over time. It is important to mention that not all twins require constant real-time data. Some operate with periodic updates when full connectivity is not practical. What matters is the loop between data, model, and action that remains active. The true power of a digital twin lies in its feedback loop. Let's picture an airport terminal or even a bridge. Sensors might count passengers, track energy use, and monitor indoor air quality. All that information is sent to the digital twin, which updates in real time. The model then runs simulations. What if passenger flows increases by 20% next month? What if one ventilation system fails? How will that affect comfort and safety inside the asset? The twin provides the answers before these situations actually occur. Operators in that case can apply the results directly to the real world, adjusting schedules, changing air conditioning settings, or even reconfiguring spaces. This continuous cycle from data collection to simulations in real-world action is what transforms the digital twin into a decision-making tool rather than a static model. It is a shift from reactive maintenance to proactive management, enabling a culture of continuous improvement. So, what are the key benefits of adopting a digital twin in the built environment? First, enhanced decision-making. Having an accurate real-time view of an asset allows engineers and managers to make data-based decisions instead of relying on assumptions. Second, predictive maintenance. Rather than waiting for a component to fail, the digital twin can alert the operator when a threshold is reached, for example, when the vibration of a bearing exceeds a safe limit. This might help to reduce downtime and extend the lifespan of critical infrastructure. Third, we might have a better operational efficiency. By analyzing usage patterns, we can optimize lighting, ventilation, or energy consumption in tunnels, buildings, or even road networks. This is not only lowers cost, but also contributes to environmental sustainability. Finally, we might increase safety. Hazardous conditions such as floods, structural fatigue, or fire propagation can be simulated safely in the virtual model before they even really happen in real life. For these reasons, digital twins are becoming essential in modern asset management. They represent a step forward from traditional inspection and maintenance toward a more connected, intelligent, and resilient infrastructure system. Just to sum up, I would like to say that digital twins combine sensing, data, and simulation to give us a powerful tool for understanding how the built environment truly behaves. If you want to know more about digital twins, in the previous QR code, you can see more information regarding the master that we are hosting. Thank you again for your attention, and we'll hope to see you in the next video of this MOOC.